So let us complete this exercise today. We have solved the first three parts so far, so this is the fourth one. Here we have to prove that the radical of an ideal I equals the entire ring if and only if the ideal I itself is equal to the entire ring. So let's solve this. So in the solution we start like this. By part 1 we have R of I equal to the entire ring if I is equal to the entire ring. Why? What was part 1? Recall that part 1 gives us this, that the radical of an ideal I contains I within it as a subset. So if I equals the entire ring, obviously R of I contains the entire ring. However, the radical of I itself is of course a subset of the entire ring. So combining these two containments, we get R of I equal to 1. That is why if this is true, then this is true. In other words, we have proved one of the two implications, namely this implies this. I have kept this part separately because I don't think it should be included in this solution. It is something very easy which we should be able to instantly think of and understand. This much is enough. It's enough to write just this much. Now we go for the other implication. For the other implication, which is this implies this, the hypothesis is this. That means this is now given. So accordingly, now let R of I be the entire ring. Now we know that everything is going to be inside R of I. In particular, the identity element 1 of the ring is also inside R of I. So by the definition of Ri, some power of that identity element will belong to I, where the exponent n is some positive integer. We are not explicitly writing positive integer because in this context that's what this means. But 1 to the power n is 1, so that way we get the fact that 1 belongs to I. But you know what happens when the identity element belongs to an ideal? It becomes the entire ring. So that way, if this is true, then this is also true. So this is the solution to part 4. Next, let's see part 5. Part 5 is this identity. This time it's not an implication. The radical of the sum of two ideals I and j equals the radical of this sum, where you see the radical of I and radical of j. So the whatever we are having here on the right hand side, that is the radical of the sum of radicals of I and j. So let's now establish this. So here also the solution starts like that, like the previous solution. By part 1, straight away we have this, that this is contained in this. But of course, let us see exactly how that is true. Part 1 gives us these two containments immediately, that I is contained in its radical and j is contained in its radical. So if we now take the sum of I and j, obviously that will be contained in the sum of their radicals. And this containment then directly implies that the radical of I plus j is contained in the radical of this sum of radicals. I am not going to say anything more about how this containment comes from this. You should be able to figure that out. It's extremely easy. Just apply the definition of radical, you will get it. So now we proved the reverse containment, that this is also contained in that. Now for the reverse inclusion, we start by taking any element in this radical. Let that be x. Then by the definition of radical, some power of x will belong to this Ri plus Rj for some positive integer n. But then x to the power n is going to look like this, a plus b, for some a coming from Ri and b coming from Rj. Now next we have this, because a belongs to the radical of I, so some power of a belongs to I, where the exponent, I means this I, where the exponent small I is some positive integer. Similarly, because b belongs to the radical of j, some power of b to the power j belongs to the ideal j for some positive integer j. Now next we are going to define two sets and let's see where it all goes. So those two sets are x and y. X is the set of all k such that k is non-negative and less than or equal to I plus j minus 1, I plus j minus 1, and k is greater than or equal to I. That condition is also there. In this context, although I haven't written that explicitly, but k is an integer. That means k is a non-negative integer less than or equal to I plus j minus 1, and at the same time k is greater than or equal to I. Do these inequalities make sense? I mean, what I am trying to say here is what type of number is I plus j minus 1? Note that I and j are both positive integers. So in the least case, both of them can be equal to 1. Even then, I plus j minus 1 is equal to 1. So this quantity is actually a positive integer. Okay, so obviously it's greater than 0 and k lies between 0 and that, and k is greater than or equal to I, and k is an integer. In the set y, this part is same as that one, but this time k is less than I. So from these two conditions you can clearly see that x and y together form a partition of the set of all non-negative integers less than or equal to I plus j minus 1. Why? Because you take any k in this range, either k is greater than or equal to I or k is less than I, and as such the union of x and y is the set of all integers in this range. And x and y are disjoint also, because no k can simultaneously satisfy these two inequalities. Now what are we going to do with these two sets? Let's see. So next we apply the binomial theorem in the ring A, which exists because A is the commutative ring. And what do we do with this theorem? We consider this power of x to the power n times I plus j minus 1. Because n and I plus j minus 1 are both positive integers, so this rule of exponent, where you can take one exponent first and then you take the other exponent, that is applicable here, in spite of A being just a ring and not a field. So that way what do we get? We get x to the power n whole to the power I plus j minus 1. And we already know that x to the power n is equal to a plus b. So that way we get a plus b to the power I plus j minus 1. And we are using the binomial theorem to expand this power. Okay. So that way we get this. You already know the structure of the binomial theorem. In this sum, the index k will vary from 0 to this exponent I plus j minus 1. Again I am repeating, I plus j minus 1 is a positive integer. And what are the terms in this sum? You see the usual binomial coefficient here, which in another notation would be read like this: I plus j minus 1 ck. Okay, it is that thing, times a to the power k times b to the power this exponent minus k. So k is the index of this summation. And we are using those sets x and y to split this sum into two parts. That is why you can see I said those things, that x and y form a partition of the set of all non-negative integers less than or equal to I plus j minus 1, because those are the integers that we see here, and that is why I have also chosen this index name k. So a part of this case will form the set x and the remaining case will form the set y, and the sum will be split into two sums. and then the conclusion is that this first sum belongs to I and this second sum is an element of J. So their sum is in I plus J. But how? Let's see. So this is the reason. If the index k is an integer in the set x, then by the definition of x, k is greater than or equal to I. Now you forget about the sum and all the other terms momentarily and only concentrate on the power a to the power k. And a to the power k can be written as a to the power k minus I times a to the power I. That other rule of exponents, the one other than this one, is also applicable here. Why? Because k is a positive, k actually is a non-negative integer. That's not a problem. K minus I is non-negative because of this inequality, and I is a positive integer. Why is 0 exponent not going to cause any problem? Because our commutative ring A also has an identity element 1. So this rule of exponents is applicable if our exponents are non-negative integers. So even if you have 0 exponent, the power will be 1, so that is already there. Alright. Now, what do we know about a to the power I? A to the power I belongs to I. Only this power. Okay, a to the power I belongs to I. This we knew before this calculation. Because I is an ideal, so multiplying this by this other element, any element of the ring, will also again land us in I. That means all these products. So now what do we have? A to the power k belongs to I, no matter what k is in x. For any k in x, this power of a belongs to I. So if you multiply that by this power of b, that will also be in I. Add any number of such products, which is what this coefficient tells us to do. This will be some integer, so that many times we have to add this. That will again be in I, and that is why this sum is in I. But how is this second sum in J? Let's see that next. So accordingly, let us take any k in Y now. Then by the definition of yk is less than I, or I minus k is greater than 0. Because this is an integer, this implies that I minus k is a positive integer. That means it's greater than or equal to 1. But then if you subtract 1 from both sides, you get this inequality. 0 is less than or equal to I minus k minus 1. Now you concentrate on this, not that one, this one, this power of b, b to the power I plus j minus 1 minus k, which is what we have here. Because I minus k minus 1 is a non-negative integer, so we can apply that law of exponent, that one that we applied just now here, and split this power into two powers, product of two powers. One of them is b to the power I minus k minus 1 and the other one is b to the power j. The fact that this is greater than or equal to 0 allows us to do so. J is already a positive integer. And now what do we know about b to the power j? The fact that b to the power j belongs to the ideal j. So if you multiply that by this power of b, the product will also belong to j because j is an ideal. That means this belongs to j. So any such power, regardless of what k is in y, is in j. So you multiply these powers of b by a to the power k, again k can be anything from y, that will belong to j, and you add any number of such products, that sum is also in j, and then you add such things again, that is in j, and that is why this is again in j. So ultimately what are we getting? We are getting the fact that this power of x belongs to I plus j. Note carefully that I plus j minus 1 is a positive integer. That is why I said that even in the least case where I and j are both 1, this is equal to 1, that means the product of n and this is also a positive integer. So some power of x where the exponent is a positive integer belongs to I plus j. So what does that mean? It means that x belongs to the radical of I plus j. That is next part we are going to write. So we write like this, that is we have this in I plus j. Now because this exponent is a positive integer, x belongs to the radical of I plus j. But what is x? X originally was any element here, which we have proved is now here also. And that way this is also a subset of this. So combining this inclusion and the previous opposite one, we finally get equality. So that solves this part. And I think there is one more. Let's see. And yes, there is one more part, part 6. In this one, p is a prime ideal, and we have to prove that the radical of p to the power n is equal to p for any positive integer n. P to the power n is the product of n copies of p. So let's see how we can solve this. So the solution starts by applying part 3. Let's recall what part 3 says. Part 3 says that the radical of the intersection of two ideals I and j equals the radical of their product ij. So this is the extended version of that, where instead of two ideals we have any finite number of ideals, and in this case all the ideals are equal to p. So this is the product that is equal to the radical of the intersection, where n copies of p are involved in this intersection. So that of course is R of p, and by part 1 we are not writing that anymore, we know that very well. This contains p, so that way we get the fact that this contains p. Now we have to prove the reverse inclusion. So let's see. For the reverse inclusion, we take any element x in the radical of p. You see, actually we are interested in this, right? We want to show that this is equal to p, and so far we have shown that this is a superset of p. Now we want to prove that this is a subset of p. But it's pointless to work with this because we have already simplified it to this. We saw by applying part 3 that this is just equal to this. So we can start by taking any element x in the radical of p. So then some power of x will belong to p for some positive integer exponent n. Do not put n here, okay, because n already is being used here. So you put something else, so n say. But x to the power n belongs to p. So x to the power n is the product of m copies of x, and when such a product belongs to a prime ideal, then at least one of the factors has to be in the prime ideal, because that's what prime ideal means. But here all the factors are x. So that way x has to belong to p. So any element here is also in p. So R of p is also a subset of p, which just means that this is also a subset of p. So combining this containment and this containment, we have equality, and that's what we wanted to prove. And let me just end the video here itself. There are quite a few other things also in this chapter. Eventually we are reaching the end of this chapter, but still there are extensions and contraction of ideals are also there. So those things will also come, and then only the exercises will start. So see you next week on the same day with further things. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.